Welcome to the Deep Dive, the show that pulls back the curtain on the invisible technologies powering our modern world. From the lightning-fast 5G connection on your smartphone to the vast global networks that keep us all connected, there are unsung heroes working tirelessly behind the scenes, enabling it all. We're talking about essential components like the power amplifier or PA. These aren't just obscure bits of silicon that only a handful of engineers pore over. They are absolutely critical to how well your devices transmit signals.
Absolutely. They affect everything.
Right, everything from the clarity of your calls to the actual battery life of your everyday gadgets. So let's unpack this. Today we're taking a deep dive into the intricate world of power amplifier characterization, especially their tricky, often misunderstood nonlinear behavior. It's a journey into the very heart of wireless communication, uncovering the complexities that make modern connectivity possible.
You've hit on the core challenge right there. In the relentless quest for ever better wireless communication, higher data rates, and crucially, longer battery life.
Which everyone wants.
Exactly. Engineers face immense hurdles getting these critical components to perform optimally without messing up signals, particularly in the demanding environments of modern wireless communication like 5G and beyond. It requires incredibly precise measurements.
Right.
And a deep, nuanced understanding of their unique characteristics. It's a constant battle against physical limitations, pushing the boundaries of what these tiny devices can achieve, all while maintaining signal integrity.
And we've got a truly fascinating stack of sources for this deep dive, from detailed lab experiment guides and technical white papers.
The real technical stuff.
Yeah, which often reveal the nitty-gritty of the challenges, to specialized application notes that show how real-world problems are actually solved.
Practical solutions.
Exactly. They'll help us understand exactly why we care so much about these measurements, how they're performed, and the cutting-edge techniques engineers are using today.
Pushing those boundaries.
Pushing the boundaries of what's possible in wireless technology. Our mission today is to give you a shortcut to understanding the hidden complexities that enable your devices to work seamlessly.
Yeah.
We're aiming for those aha moments and maybe some surprising facts about the very foundation of wireless tech.
Hopefully demystify it a bit.
Right, turning you into someone much more informed about the invisible workhorses discreetly powering the tech in your pocket. Let's start with something you interact with every single day, perhaps even right now, your smartphone.
Can't live without it.
It's truly one of the most indispensable personal items in modern life, packed with a wide variety of applications that benefit us in countless ways. But have you ever paused to think about how it actually talks to the world?
How that magic happens.
Yeah, how does your voice, your text messages, or that high-resolution video you just shared actually get from your device to another across miles of air? At its core, the power amplifier, or PA, is absolutely fundamental to this process.
Absolutely.
It plays a key part in driving the antenna on the transmitting end,
Giving it the push.
literally boosting and sending out your calls, texts, and data signals into the air with enough strength to reach a cell tower or another device. Conversely, on the receiving end, you've got a low-noise amplifier, or LNA,
The LNA, right?
that takes those incredibly tiny incoming signals and boosts them up so your phone can understand and process the information.
So you can actually hear the other person or get the data.
Exactly. Together, these two components, the PA for sending, the LNA for receiving, form the basic operational backbone of what's called a duplexed communication system.
Sending and receiving at the same time, basically.
Right. It's a beautifully orchestrated dance of signal amplification and reception happening constantly, often without you even realizing it.
What's truly fascinating here is how this seemingly simple concept of amplification connects so deeply to the broader wireless market and its relentless evolution.
It's amazing how far we've come.
It really is. Over the decades, this market has seen truly remarkable development, from the very first clunky handheld phone introduced by Motorola.
The brick phone.
Yeah, the brick. We've come light years, moving through generations like 2G, 3G, 4G, and now 5G. This continuous thirst for better wireless transceiving system design, meaning better ways to send and receive signals, combined with the relentless drive for lower market costs, has become a primary goal for modern RFIC.
Radio frequency integrated circuit.
Exactly, RFIC manufacturers. Every new generation of wireless technology, like the transition to 5G, with its demands for higher data rates and lower latency,
The pressure is always on.
it just ratchets up the performance expectations and technical demands on these tiny but mighty components, making their design and characterization an increasingly complex, art and science.
And this is where the real ingenuity comes into play, because engineers aren't just trying to make these PAs powerful. They're constantly grappling with a fascinating, almost contradictory balancing act.
A real trade-off.
In PA design, two characteristics stand out as paramount: efficiency and linearity. It's a fundamental trade-off that engineers are constantly wrestling with.
It really is.
A push and pull that dictates so much of your device's overall performance.
And understanding why these two factors are so crucial is absolutely key to appreciating the engineering challenge.
Okay, let's break it down.
First, let's talk about efficiency, often measured as PAE, or power added efficiency.
PAE, got it.
This is directly about maximizing battery life. Think about it. Every bit of electrical power consumed by the PA that isn't converted into useful radio frequency output power is essentially wasted.
Just turns into heat.
Exactly. Dissipated as heat. This wasted energy means your phone dies quicker, your device runs hotter, and its operational life is shortened.
Nobody wants a hot phone that dies fast.
No. So engineers are constantly striving to increase PAE so that your devices can last longer on a single charge. That directly translates to a better user experience and, in a fiercely competitive market, a significant advantage.
Higher efficiency means more talk time, more streaming.
More productivity, yeah. It's a huge deal. Second, and equally vital, is linearity.
Okay, linearity.
Signal quality. Precisely. This is all about signal quality. Ideally, PAs are designed to operate within their linear region.
Meaning?
Meaning the output signal is a faithful amplified replica of the input. No added distortion, no unwanted noise, just a bigger version of what went in.
Makes sense.
However, to achieve higher power efficiency, that goal we just discussed, PAs are often driven into their nonlinear regime.
Okay, so you push them harder for efficiency.
Right, but that's where things get tricky. Operating nonlinearly introduces distortion.
So the output isn't a perfect copy anymore.
Exactly. The output signal is no longer a perfect copy of the input. This directly affects signal demodulation.
How the receiving device reads the signal.
Making it harder for the receiving device to correctly interpret the digital data encoded in the signal. This then impacts the bit error rate.
Errors in the data.
Which, in turn, directly impacts how clearly and reliably information is received. If the signal is too distorted, the receiving device simply can't make sense of the data.
Leading to dropped calls, slow downloads.
Corrupted data, all that bad stuff. A critical and often visually striking consequence of this nonlinearity is what we call spectral regrowth.
Spectral regrowth. Okay, what's that like?
Imagine a pristine, perfectly tuned musical note from a concert grand piano.
Okay.
Now, if you take that note and play it through a cheap, overloaded speaker, it distorts, right?
Yeah. Sounds fuzzy, maybe crackly.
Exactly. Suddenly you're hearing not just the clear, intended note, but fuzzy, out-of-tune harmonics and overtones bleeding into other frequencies that weren't part of the original sound.
Got it.
That's essentially what spectral regrowth does in a wireless system. It takes your carefully contained wireless signal and causes its energy to spill over into adjacent frequency bands.
Creating unwanted interference.
Exactly. Where other communications are happening, this is not just an inconvenience, it necessitates stringent linearity requirements.
So that's why engineers worry about it so much.
Precisely. It's why you hear engineers talk about metrics like ACLR for WCDMA, EU2 for LTE, and ACPR for CDMA2K.
Okay, those acronyms measure this spillage.
Pretty much. They're all about ensuring signals stay clean and in their designated lanes on the radio spectrum, preventing them from interfering with other users or services. In a world where spectrum is finite and demand is exploding,
Which it totally is.
every bit of spectral regrowth means wasted bandwidth, fewer users, and slower speeds across the network. It's a huge deal for network operators.
So what does this all mean for you, the user, sitting there with your device?
Yeah, bringing it back.
It means PA design isn't just about achieving maximum raw power. It's about satisfying these complex vendors of merit, like PAE for battery life and TOI, or third-order intercept points, which dictate the level of nonlinearity.
Right, quantifying that distortion.
Since PAs often operate under large signals and are specifically driven into the nonlinear regime to achieve that crucial efficiency,
That balancing act again.
characterizing this nonlinear behavior with extreme precision is of utmost importance to any RF engineer. It's the difference between a crisp, clear call that lasts all day.
And a dropped connection on a device that dies by noon.
Exactly. These seemingly abstract technical parameters directly translate into your everyday wireless experience.
Beyond efficiency and basic linearity, designers use even more specific, quantifiable metrics to characterize this tricky nonlinear behavior with greater precision.
Okay, like what?
One of the most critical and widely used metrics is the 1 dB compression point.
Okay, 1 dB compression point.
This is the input power level where the amplifier's gain drops by 1 dB from its ideal linear gain.
So start to strain, basically.
Exactly. It's a crucial point because it marks the boundary where the amplifier starts to lose its linearity and begin compressing the signal. As you push more power in, you get less than a proportional increase in output.
Oh, okay.
We saw this directly in our lab context source, where measuring this point for the Gali 1 Plus amplifier was a key part of its characterization. It offers a tangible benchmark for where its linearity begins to break down. Then there's ACPR, or adjacent channel power ratio.
ACPR, we mentioned that briefly.
Right. This bench of merit describes the ratio of transmitted power on the assigned channel to the power received in an adjacent radio channel after it goes through a receive filter.
So measuring that spillover again?
Precisely. It's the industry standard for quantifying out-of-band distortion characteristics, directly measuring how much one channel might interfere with another. In the dense landscape of wireless communication where channels are packed closely together,
Super crowded airspace.
this is especially important for standards like UMTS and LTE, where spectral purity is paramount to avoid interference and maintain overall network capacity. A poor ACPR means your signal is effectively shouting into your neighbor's channel. And finally, EVM, or error vector magnitude.
EVM, okay.
This metric quantifies the overall PA nonlinearity, and it's absolutely crucial because, as we mentioned, nonlinear response directly affects signal demodulation and the bit error rate.
Right, the quality of the receives data.
Exactly. For demanding modern standards like 5G, which rely on complex modulation schemes to pack more data into every signal,
Getting more bits through the air.
EVM and ACPR function as key benchmarks for compliance with the demanding new specifications. These metrics are not just about raw power, but about the quality and integrity of the signal itself.
Directly impacting how much data can be reliably transmitted and received. These aren't just abstract numbers engineers pore over. They are the fundamental benchmarks for performance, quality, and value.
They really are.
They tell us precisely how clean, how reliable, and how efficient the signal from your device will be. It's the hidden language of signal integrity
That engineers obsess over.
that engineers obsess over to give us the seamless wireless experiences we've come to expect and demand. If these numbers aren't met, your device simply won't perform as advertised.
Or worse, it could degrade the entire network for everyone nearby.
Right, exactly.
Now, in the field of microwave engineering, S parameters are absolutely fundamental.
Test parameters, okay, I've heard of those.
Yeah, they characterize how power flows through a device, how much is transmitted, how much is reflected, and they work perfectly for understanding linear behavior.
Okay, linear only.
In the lab experiment we reviewed, the first step was actually to measure these small signal S parameters to verify they match the datasheet provided by the manufacturer.
A standard first check.
Exactly. It's a standard and necessary initial check for any RF component. However, here's the critical point, and it's a profound limitation. S parameters are inherently restricted to linear device characterization.
Ah, okay, so they break down.
They cannot adequately capture or predict how a device will behave once it's driven into its nonlinear operating region.
Why is that?
Because S parameters, while foundational for understanding linear power flow, fundamentally assume a proportional relationship between input and output. They're based on small signal analysis,
Low power levels.
where the device behaves predictably and proportionally. The moment you push a PA hard, driving it into saturation or compression, that linear relationship completely breaks down. You start generating harmonics and intermodulation products, those unwanted frequencies we talked about with spectral regrowth,
Stuff you don't want.
that the linear S parameter model simply cannot predict or account for. It's like trying to model complex turbulent water flow with a simple, smooth laminar flow equation.
The math just doesn't fit the reality anything.
Exactly. The math just doesn't capture the chaotic and non-proportional reality of a nonlinear PA.
That's a perfect analogy. It's like trying to understand how a high-performance sports car handles at its absolute limits, accelerating at full throttle, braking hard into a corner,
Pushing it hard.
pushing the tires to their very edge by only observing its behavior while cruising gently at a constant low speed on a flat highway.
Yeah, you'd miss everything interesting.
You'd completely miss the critical dynamics of acceleration, braking, and cornering under stress when the engine is revving, the tires are gripping, and the chassis is flexing. Our sources clearly show that while small signal S parameters might appear linear across a particular low power range,
They look fine down low.
a large signal power sweep measurement quickly reveals significant gain compression and distortion, proving their inadequacy for characterizing nonlinear PAs.
Especially at high input and output power levels.
Right. That low-speed cruising data just doesn't tell you enough about the car's true capabilities under real-world racing conditions.
Precisely. This limitation is why engineers absolutely need more advanced parameters and measurement techniques.
Beyond S parameters.
Exactly. Our sources actually mention X parameters as a promising future solution specifically designed for characterizing nonlinearity.
X parameters, okay.
Going far beyond the traditional S parameter approach by capturing these complex nonlinear dependencies. This continuous evolution of measurement science is not just an academic exercise. It's vital as devices become more complex, more efficient, and operate in increasingly demanding environments.
Always pushing the envelope.
Hmm.
So we've established why these PAs are so critical and the inherent tension between efficiency and linearity.
Yeah, that fundamental tug of war.
We've seen that traditional S parameters fall short when trying to characterize them at their operational limits.
They just don't cut it for the nonlinear stuff.
But the real question then becomes, how do you even begin to measure these incredibly subtle and complex nonlinear behaviors? What tools were engineers relying on before the modern era?
Right, what was the state of the art, say, 15, 20 years ago?
And how have those tools evolved as wireless technology has exploded?
Historically, for many years, characterizing PA nonlinearity involved time domain measurements.
Time-domain, okay.
Primarily using a vector signal analyzer, or VSA, and a vector signal generator, or VSG.
VSA and VSG, got it.
The VSG would generate the complex modulated input signal for the device under test, or DUT.
Simulating a real signal.
Right, simulating a real-world wireless signal. The VSA would then capture the output signal, analyzing it over time to calculate those critical metrics we discussed earlier, like EVM and ACPR.
Okay.
This approach was certainly satisfactory for older communication system generations, think 2G or 3G.
Served its purpose back then.
It did for many
It
years.
sounds logical, doesn't it? Generating a signal, measuring the output over time, and then analyzing it to see what's happening.
Seems straightforward enough.
But as technology advances, the demands on measurement tools and techniques also evolve significantly. What worked reliably yesterday might very well be a major bottleneck today.
Definitely.
You mentioned 5G new radio earlier. I can only imagine the challenges it presented to this traditional VSA method.
You're absolutely right. The VSA method, while foundational, came with significant limitations, especially with the ever-increasing demands of 5G new radio, or NR, systems.
Okay, like what kind of limitations?
One major issue is signal-to-noise ratio, or SNR degradation.
SNR, signal versus noise.
Right. As signal bandwidths get wider, a hallmark of modern communications, particularly 5G, which uses very wide channels,
Huge bandwidths now.
the system's SNR inherently degrades. This makes it harder to distinguish the true signal from background noise,
The noise floor comes up, basically.
which in turn limits the minimum EVM that can be reliably measured. Additionally, random noise at low power levels can significantly degrade accuracy and reliability of EVM measurements.
Making it hard to see the subtle stuff.
Exactly. Difficult to get a true picture of the PA's subtle, nonlinear performance at lower drive levels. Then there's calibration complexity.
Calibration. Always tricky.
Calibrating a VSA setup is notoriously intricate and time-consuming, and this complexity can easily introduce systematic errors.
Errors baked into the measurement itself.
Right, especially when dealing with very wide bandwidths or DUTs with poor impedance mismatch. Achieving high signal fidelity.
Making sure the signal going in is perfect.
Precisely. Ensuring the signal reaching the DUT is clean and precisely known becomes challenging due to factors like signal loss in long, lossy cables at higher frequencies or reflections. Even advanced calibration techniques often involve trade-offs, where solving one error vulnerability might inadvertently introduce another.
A whack-a-mole situation.
Kind of, yeah. It's a constant battle for pristine accuracy that required meticulous attention and deep expertise. Measurement speed is another critical factor.
Time is money in the lab.
Absolutely. Digitizing wideband input signals without introducing distortion or aliasing requires high-speed analog-to-digital converters and immense computational power.
Lots of processing.
This process is inherently intensive and can drastically slow down the entire measurement process, especially for the iterative tests required during design and characterization.
You need to test, tweak, test again.
Exactly. In an industry driven by rapid innovation and short design cycles, waiting for measurements to complete can be a significant drag on product development. And finally, there's the issue of equipment overhead.
Meaning you need a lot of gear.
Pretty much. The traditional time domain setup requires multiple primary pieces of equipment: a dedicated VSG for signal generation, a VSA for signal analysis,
Okay.
and often a separate VNA vector network analyzer for other linear parameters like S parameters.
So 3 big boxes, potentially.
At least. This means unique cabling, multiple power supplies, and separate calibration routines for each device. This increases test hardware, software licensing, and peripherals. It also significantly extends device testing time due to the need for serial switching between instruments and repeated recalibrations.
Switching cables, running new CALs.
It's a cumbersome, multi-step process, almost like assembling a different, complex jigsaw puzzle for every single test scenario.
A jigsaw puzzle indeed. That sounds like a lot of moving parts, a lot of potential for error, and frankly, a ton of time spent in the lab.
It wasn't ideal.
It's clear that the system, while foundational, simply couldn't keep pace with the relentless demands of modern innovation, could it?
No, 5G really pushed it over the edge.
Those traditional time domain measurements sound incredibly painful for engineers, especially with 5G pushing the limits. So how did the industry respond? What was the game-changing shift?
The shift was really moving away from pure time domain analysis for this. That's precisely the right question. The industry needed a more streamlined characterization scheme, and it evolved dramatically by moving from the time domain into the frequency domain.
Frequency domain, okay.
Enter Keysight's vector component analysis, or VCA, method. This approach dramatically improves access to and accuracy of those critical figures of merit we've been discussing for nonlinear behavior. The core innovation here is leveraging the Vector Network Analyzer, or VNA.
The VNA, which we said was usually for linear stuff like S parameters.
Exactly. Leveraging the VNA in conjunction with specialized modulation distortion, or MOD software.
MOD software, okay.
This transformation turns the VNA into a powerhouse for nonlinear characterization, essentially getting far more out of existing highly accurate instrumentation by expanding its capabilities. The benefits of this approach are truly profound, addressing almost all the limitations of the older methods.
Okay, let's hear them.
First, you get an integrated single connection multiple measurement setup.
One connection, multiple tests. Sounds good.
Imagine using the same physical setup and connection to measure linear parameters like S parameters, gain compression, and noise figure, alongside nonlinear metrics like IP3, and D, those critical modulation distortion metrics like EVM and ACPR.
All in then go.
All possible on a VNA with the MOD software, achieving a one setup, one connection, all calibration approach.
Wow.
This greatly simplifies test setups, eliminates the need for unique cabling and multiple expensive devices, and radically reduces test time.
Huge time saver.
No more reconnecting or recalibrating for each different test. Second, it offers unparalleled accuracy and repeatability.
Better data.
The VNA's state-of-the-art calibration techniques are leveraged to precisely remove any contributions of the test setup from the measurement itself.
Taking the test gear out of the equation.
Exactly. This includes advanced corrections for input port mismatch, channel power, and IQ data, yielding a truly flat, known input signal at the device under test. Because the measurement is coherent, meaning the VNA's receiver is precisely synchronized with its source and the applied modulation.
Everything's timed perfectly.
Every trace is inherently consistent, delivering superior reproducibility and trustworthiness in the data. Engineers can be incredibly confident in their results. Third, it achieves the lowest residual EVM on the market.
Lowest error, basically.
Right. The MOD application's architecture is specifically designed to isolate the distortion contributions specifically from the DUT, separating them from the instrument's own imperfections.
So you're really seeing the device, not the tester.
Precisely. By having a much wider system dynamic range and a significantly lower noise floor compared to traditional VSA setups, it purifies the PA characterization.
Yeah.
It reveals the true, unmasked performance of the PA rather than having that performance obscured by system noise or instrument limitations.
Letting engineers see the subtle distortions that truly matter.
So how does this ingenious system actually work?
Yeah, how does it do it?
The VSG still provides the wideband modulated input signal to the DUT as before.
Okay, still need the signal source?
However, the MOD application within the VNA doesn't capture the entire wideband signal in the time domain. Instead, it measures the input and output signal tone by tone in the frequency domain.
Ah, frequency by frequency.
Right. The VNA then coherently stitches these individual frequency measurements together, performing precise math across a wide spectrum.
Building up the picture.
To achieve a wideband coherent measurement of the modulated signal, the measured output signal is then meticulously decomposed into its linearly and nonlinearly correlated components,
Separating the good from the bad distortion.
from which EVM and ACPR are precisely calculated. It's a much more surgical, frequency domain approach to capturing and analyzing complex modulated signals. The VCA method further expands measurement capabilities with additional software applications that integrate seamlessly into the VNA platform.
More tools in the toolbox.
One such powerful application is ALC, or arbitrary load control.
ALC, load control. What does that mean?
In real-world applications, PAs rarely operate under ideal normalized loads. Think about the highly variable load conditions encountered in massive MIMO and beamforming architectures.
Where the antenna environment changes constantly.
Exactly, where the impedance seen by the PA can change dynamically. ALC allows the VNA to quantify PA variable load behavior by continuously shifting the load impedance presented to the PA while measuring its performance.
Simulating those real-world conditions.
Right. This characterizes worst-case DUT, EVM, and ACPR under realistic dynamic conditions. This provides highly accurate sensitivity and performance metrics that are invaluable for designers.
Understanding how it behaves under stress.
Ensuring robust designs for diverse, non-ideal conditions. Another crucial capability is DPD, or digital pre-distortion analysis.
DPD. Okay, pre-distortion. What's that?
To meet increasingly stringent linearity and efficiency demands, especially in 5G, designers often use DPD. It's a very clever technique.
How does it work?
It deliberately distorts the modulated input signal before it even enters the amplifier.
Wait, you distort it before it goes in?
Yes, but with the inverse of the PA's expected distortion.
Ah, okay, so you're predicting the PO's bad behavior.
And counteracting it in advance. The idea is that when this pre-distorted signal hits the nonlinear PA, the PA's inherent nonlinearity will correct the pre-distortion,
Canceling itself out.
resulting in a linearized, clean signal at the PA's output, essentially making a nonlinear amplifier act much more linearly, even when driven hard for maximum efficiency.
That's brilliant.
The VNA with MOD can then precisely analyze this DPD process, generating the optimal pre-distortion coefficients. What's truly insightful here is that this technique fundamentally shifts a significant portion of the linearity problem from complex, inflexible analog hardware
Hard to change.
to flexible, programmable digital signal processing, which is far more adaptable and scalable.
That's a fascinating shift in design philosophy.
Yeah.
Moving the fix into the digital domain. These advanced capabilities are absolutely crucial for optimizing PA performance to satisfy the ever-increasing demands of cutting-edge technologies like 5G.
Absolutely essential now.
With its millimeter wave carrier frequencies, incredibly wide bandwidth signals, and complex modulation schemes, it's about building in performance and correction right from the design phase.
Using this precise measurement as the critical feedback loop.
So, if I'm understanding this correctly, the VNA, traditionally known for linear measurements, has effectively evolved into a comprehensive nonlinear characterization powerhouse.
Precisely.
Yeah.
Ultimately, the VNA with the MOD application offers a wide dynamic range, easy and highly accurate calibration that ensures signal fidelity at the DUT input.
Trustworthy measurements.
Seamless compatibility with simulation environments like Keysight Pathwave Advanced Design System, ADS, to accelerate design cycles.
Connecting design and tests.
And sophisticated software for analyzing distortion under real modulated conditions. It's truly an essential tool for fully characterizing both the linear and nonlinear performance of power amplifiers.
Pushing the boundaries of what these devices can achieve, and ensuring the quality and reliability of our connected world.
Couldn't have said it better myself.
Okay, let's unpack this next bit. So far, we've mostly talked about signals as if they're continuous streams, like a constant carrier wave.
Right, continuous wave or CW signals?
But sometimes our devices don't just send out a continuous, steady signal. Think about radar, for example,
Be pulses of energy.
or even some aspects of modern cellular communication, especially in high-speed data transmission or certain access methods. Signals often come in rapid bursts or pulses
On and off, on and off.
rather than a constant stream. This isn't just an edge case, is it?
No, not at all. You've hit on a critical point. In many real-world scenarios, power amplifiers operate under pulsed RF conditions.
Pulsed RF.
Okay. This means they transmit high-peak power signals for very short durations, followed by longer off periods, essentially a low-duty cycle.
High power, but only for a short time.
Exactly. This isn't just an occasional operating mode. It's a fundamental requirement for many critical applications, particularly in defense, avionics, and advanced wireless communication. There are several critical reasons for performing these pulsed measurements. First, it's about simulating true operating environments.
Testing it like it's used.
Right. It accurately reflects how PAs operate in systems like radar, electronic warfare, and modern wireless communication systems where burst transmissions are common. For managing power, avoiding interference, or achieving specific communication protocols, you simply must characterize the device under the actual conditions it will encounter.
Not just an idealized continuous wave scenario.
Correct, which might give you misleading results. Second, and vitally important, is protecting the device under test, or DUT.
Keeping the expensive chips safe.
Exactly. Continuously running a PA at high power with a continuous wave, or CW signal, can generate excessive heat,
It would just cook itself.
potentially overheating and even destroying the device during characterization. This is especially true for high-power PAs. Pulsed measurements allow the PA to achieve its high peak power output, its maximum capability, without generating that excessive sustained heat,
Letting it cool down between pulses.
preventing thermal damage during the often lengthy characterization process. It's a fundamental safety measure for both the expensive DUT and the test equipment itself. And third, it ensures accurate characterization of dynamic behavior.
Seeing how it behaves when switching on and off.
Precisely. By simulating the real-world pulsed operation, engineers get a much more realistic and accurate picture of the PA's dynamic behavior. How it responds when it's rapidly turned on and off, how its gain and phase shift over the course of a pulse, how quickly it settles.
Capturing those transient effects.
Right. This level of detail, capturing transient effects and power-up, power-down characteristics, is simply not captured with continuous wave measurements, which only give you a static, steady-state view.
It's the difference between a still photograph and a high-speed video.
That's a great analogy.
That makes perfect sense. Okay, when we talk about pulsed signals, there are a few key terms that help us define and understand them. Could you walk us through those?
Certainly. First, we have pulse width, or PW.
PW, pulse width.
This is simply the duration that the RF signal is actually on or active. It's how long the burst of energy lasts. For radar, this might be microseconds or even nanoseconds. Very short. Next, we have pulse repetition period, PRP, which is also sometimes called the pulse repetition interval,
PRI.
PRP or PI.
Got it.
This is the total time duration from the start of one pulse to the start of the next pulse. So it includes both the on time, the pulse width, and the off time between pulses in a single cycle. Then there's pulse repetition frequency, PRF.
Okay.
This is simply the inverse of the PRI. It tells you how many pulses occur per second.
How often the pulses repeat.
Exactly. So if your PRI is 1 millisecond, your PRF is 1 kilohertz, meaning you have 1,000 pulses per second. It's the rate at which the pulses are transmitted. And finally, duty cycle.
Duty cycle. Heard that one before.
This is a crucial parameter defined as the pulse width, PW, divided by the pulse repetition period, PRI, and then often expressed as a percentage.
The percentage of time it's on.
Exactly. It's essentially the percentage of time the signal is active or on. For example, a 100% duty cycle is equivalent to a continuous wave, or CW, signal.
Always on.
While a 10% duty cycle means the pulse is on for 1/10 of the overall pulse period and off for the remaining 9/10. This duty cycle significantly influences the thermal stress on the PA, as we discussed.
Lower duty cycle means less heat.
Generally, yes. And it also dictates how its spectral energy spreads out in the frequency domain, which is a critical consideration for designers, as we'll see.
That helps paint a very clear picture of the timing aspects.
Right.
So with these defined pulses, how do engineers actually measure inside them? It's not just on or off, right? There's structure.
Right. There's detail within the pulse itself. How do you analyze that internal structure and dynamic behavior? Absolutely. With pulsed RF measurements, we're not just looking at the overall signal. We can delve deeply into its internal structure and dynamic behavior. This leads to two primary measurement techniques.
Okay.
First, point and pulse measurements.
Point and pulse. Sounds like a snapshot.
It is. Here, a single data point, like an S parameter value, is acquired for each carrier frequency, but critically, it's acquired only during a specific, very narrow gated window.
A small time slice.
And at a precise delay within the pulse itself. The analyzer effectively takes a very quick snapshot during a specific, stable part of the pulse. The data is then displayed in the frequency domain, showing the magnitude and phase of transmission and reflection at that exact point in time within the pulse.
So you get the frequency behavior at one moment.
Correct. Ideal for verifying parameters under stable, high-power conditions without overstressing the device. Second, we have pulse profile measurements.
Pulse profile. Sounds like the whole shape.
Exactly. Instead of sweeping frequency, for this measurement, the carrier frequency is fixed. We then acquire data at uniformly spaced time positions across the entire pulse.
Stepping through time within the pulse.
By varying the delay of the measurement relative to the pulse's start, the data is then displayed as the magnitude and phase of the pulse versus time.
Showing how it changes over the pulse duration.
Right. This allows engineers to see how the characteristics of the signal change dynamically throughout the duration of the pulse itself, how quickly the gain rises, if there's any droop or compression during the pulse, and how fast it falls. It gives you a dynamic picture of the PA's response.
Those techniques are incredibly clever. They essentially allow engineers to take either a precise snapshot or a full cross-section movie of the pulse as it unfolds.
Good way to put it.
This ability to capture specific moments or the entire dynamic progression reveals critical dynamic behavior like settling times, rise and fall characteristics, and transient effects that continuous measurements would completely miss.
Things you only see when it's switching.
It's truly like distinguishing between a single flash photo and a slow-motion video. I imagine the duty cycle plays a huge role in how effectively these measurements can be made, sensitivity-wise.
It absolutely does. The duty cycle of a pulse, which we just defined, has a significant impact on the dynamic range of a measurement system.
How much range you have between the signal and the noise.
Exactly. And this is where modern VNAs truly shine compared to older equipment. With older systems, like the HP 8510C, which typically used wideband detection,
Measuring everything at once.
the dynamic range remained relatively constant, around 70 duties, regardless of the duty cycle. This was a limitation because the wideband detection method essentially measures the average power over the entire pulse period,
Including the off time.
including the off time where there's just noise and no signal. So the noise effectively limits the measurable dynamic range, especially at low duty cycles where the signal is off most of the time. For modern VNAs, however, employing narrowband detection,
Focusing on just the signal frequency.
which is much more precise and sensitive as it focuses specifically on the signal's narrow frequency slice, the dynamic range does decrease as the duty cycle gets lower.
Okay, why is that?
Think about it. If the signal is only on for 1% of the time, the average power hitting the detector over a given measurement interval is much lower, even if the peak power during the pulse is very high.
Less energy overall.
Right. This makes the inherent noise floor of the instrument appear relatively higher in comparison, effectively squeezing the available dynamic range for that specific measurement, specifically for every factor of 10 decrease in duty cycle.
Like 10% down to 1%.
We theoretically see a 20 dB reduction in dynamic range because the average signal energy available for detection has dropped proportionally. Despite this reduction with lower duty cycles, the PNA's inherently higher dynamic range.
Its baseline sensitivity is better.
Exactly. Its fundamental sensitivity is just so much better that even when affected by duty cycle, it often means it surpasses older wideband systems. The crossover point, where the PNA's performance matches or exceeds the older 8510cc systems, is approximately at a 0.1% duty cycle.
So for most common pulsed applications.
Right. For duty cycles of 0.1% or more, the PNA typically has an equal or even better dynamic range than the older 8510C systems, despite the theoretical reduction.
Here's where it gets really interesting for practical applications, though. Not only does the PNA often boast a better dynamic range for duty cycles that are common, but it also has the distinct advantage of being able to measure much narrower pulses than older systems, like the 8510cc.
Capturing those really short bursts.
Right. This provides crucial detail for very short, high-power bursts, which are increasingly common in advanced radar and next-generation wireless systems. And to top it off, it's significantly faster. One comparison showed the PNA sweeping 6 times faster while simultaneously offering 10 dB better dynamic range for a bandpass filter measurement.
Huge improvement.
That's not just an incremental improvement. That's a massive leap in both efficiency and capability for engineers in the lab.
You're absolutely right that speed and precision are game changers. Now, there's another wrinkle with pulsed signals. When a signal is pulsed, its energy isn't confined to a single, narrow frequency, even if the underlying carrier frequency is fixed.
It spreads out.
Yes. In fact, a shorter pulse, by its very nature, means its spectral energy spreads across a wider bandwidth in the frequency domain. Also, the spacing of the spectral components in the frequency domain is directly equal to the pulse repetition frequency, or PRF.
Okay, so pulsing creates sidebands related to the PRF.
Exactly. This phenomenon introduces a significant challenge: spectral contamination.
Spectral contamination sounds bad.
It is. Other unwanted spectral components, which are sidebands generated by the pulsing itself, can interfere with the measurement of the desired signal, muddying the data and making accurate characterization extremely difficult. This is where spectral nulling comes in.
Nulling them out.
It's the critical process of carefully filtering out these undesired components to isolate the true signal. Without effective nulling, your measurements will be inaccurate.
Because you'd be measuring the pulsing artifacts, too.
Right, you'd be seeing artifacts of the pulsing itself rather than the true behavior of the device.
Think of it like trying to hear a specific instrument, say a solo violin, in a very noisy orchestra that's playing a cacophony of sound.
Good analogy again.
If you can't filter out the surrounding noise, effectively the trumpets, the drums, the entire string section playing something else, your desired violin solo gets masked, or even completely overwhelmed.
Muffled or lost.
That's exactly what happens if you don't perform proper spectral nulling. And I imagine these sources of contamination can be quite complex.
They can be, yes. Sources of this contamination can include a few things. First, aliased spectral components.
Aliasing, like in digital audio.
Similar concept. For very narrow pulses with broad frequency content, the unfiltered pulsed signal can wrap around or fold back into the analyzer's receiver,
Due to the sampling process.
creating new, unwanted spectral components that appear at the wrong frequencies, making it seem like there's a signal where there isn't. Second, you have harmonics of video feed-through.
Video feed-through. Sounds old school.
It's a legacy term dating back to early radar systems, but it refers to leakage of the baseband modulation signal onto the pulsed RF signal, creating additional interference. Still a practical concern. And third, receivers themselves can have sensitivities to image and local oscillator, LO, images,
External stuff in the analyzer.
which also add to the overall noise and distortion that contaminates your measurement, especially at higher frequencies. The solution often involves advanced filtering, specifically at the intermediate frequency IF stage of the analyzer.
Eye filtering, okay.
While standard filters have limitations in their ability to precisely remove these unwanted spectral components, advanced PNA options, such as option H31,
Specific feature.
allow for custom IF filters. These custom filters can be precisely designed and aligned with the PRF, essentially creating a notch filter at exactly the frequency of the contaminating sidebands.
Targeting the interference precisely.
To achieve optimal spectral nulling, this even allows for wider IF bandwidths without introducing contamination, which translates directly to faster and more accurate measurements.
Faster because you don't need superneural filters.
Exactly. This ability to precisely manage the spectral content is absolutely crucial for clean, reliable pulsed RF measurements, especially as pulse widths become shorter and PRFs increase in modern systems.
So we've discussed the theory and the how-to of these incredible pulsed measurements. Really sophisticated stuff.
It is, yeah.
But in the real world, in the lab, what are the practical considerations engineers need to keep in mind to ensure their measurements are not just fast, but genuinely accurate and reliable? Calibration, I imagine, is paramount.
You're absolutely right. Calibration is always vital for accurate measurements, and for pulsed RF, it's no different. In fact, it can be even more critical.
More complex because of the pulsing?
Well, the methodology itself for performing an S-parameter calibration is identical to normal continuous wave, or CW S-parameter measurements.
Okay, same steps.
But the crucial point is that calibration must be performed under pulsed conditions. You cannot calibrate with a continuous signal and then expect accurate results when measuring pulses.
Why not?
Because the behavior of the system, including the test leads and fixtures, can change under pulsed operation due to thermal or electrical loading effects.
Yeah.
Things heat up differently, impedances might shift slightly.
Ah, so the setup behaves differently pulsed versus CW.
Exactly. You need to calibrate under the same conditions you measure under.
This emphasizes the extreme precision needed here.
Yeah.
So, if I'm understanding this correctly, each unique set of pulse and gating conditions,
Different pulse width, different duty cycle.
and even different power levels, requires a separate calibration. That sounds like a lot of work.
It can be.
This ensures that the measurement setup itself isn't introducing errors or distortions into the pulse characteristics, which could easily skew your results.
Making you think the DUT is doing something weird when it's actually the test setup.
Right, effectively measuring the test setup's artifacts rather than the DUT's true behavior.
Precisely. And that's where electronic calibration, or eCal modules, become incredibly useful for pulsed RF measurements.
eCal, making it easier.
Much easier. With numerous measurement setups often required due to varying pulse conditions, perhaps testing different pulse widths, duty cycles, or power levels, eCal modules dramatically simplify the process. They can be calibrated quickly with a single connection, often just a single button press on the VNA.
One button press versus swapping standards.
Exactly. Making the process much faster and more straightforward than using cumbersome and time-consuming mechanical calibration standards, which require connecting and disconnecting multiple physical standards.
Oh, click.
Yeah. eCal significantly boosts lab throughput, allowing engineers to run many more tests in a given time frame. Beyond calibration, a key practical concern, especially when dealing with high power, is protecting the device under test, or DUT,
Don't fry the chip.
and the measurement equipment itself. A crucial feature to look for in a network analyzer is its ability to keep the power constant during retrace.
Retrace, when it finishes a sweep.
Right, when the sweep is returning to the start frequency after a measurement or during band changes. This constant power delivery significantly reduces the possibility of destroying the DUT or damaging the analyzer due to sudden power fluctuations or unintended spikes. Older Agilent models, like the 8753E and 8720E series, were specifically designed with this in mind, maintaining constant power except for brief, intentional blanks during band changes.
So, avoiding sudden power jumps or drops during those transitions. That analogy about the car engine hitting erratic revs perfectly illustrates the risk. But beyond just protecting the physical hardware, how does this constant power delivery, or the lack of it, impact the quality of the measurement data itself?
Good question.
Does it introduce subtle errors that are hard to track down if the power isn't stable?
It absolutely does. Instabilities in power delivery can introduce subtle, hard-to-diagnose errors.
Like what?
A non-constant power during retrace can cause the DUT to operate outside its intended range momentarily, leading to unexpected thermal shifts or changes in impedance that then affect subsequent measurements.
So the starting point for the next measurement is off.
Potentially. These can manifest as inconsistent or non-repeatable data points, which are incredibly frustrating for engineers trying to achieve precision.
Chasing ghosts in the data.
Exactly. So it's not just about protection, it's fundamental to measurement integrity. Another important safety and accuracy measure is correctly determining and setting the signal level for the R channel.
The reference channel.
Right, the reference channel for the measurement. This is the signal that the analyzer uses to compare against the output from the DUT. If the signal level is too low on the R channel, it can be affected by the analyzer's inherent noise floor,
Gets lost in the noise.
leading to phase locking problems and ultimately inaccurate measurement results. Conversely, if it's too high,
Too much power.
it can cause receiver compression, where the receiver itself distorts the signal because it's overloaded.
The analyzer itself starts misbehaving.
Right. This leads to inaccurate readings and potentially even damaging the sensitive receiver components. Engineers must carefully consult the analyzer specifications.
Check the manual.
A typical optimal range might be 0 to nanosecond dBm and add external attenuation as needed to achieve the proper level at the R channel input.
Getting the level just right.
Ensuring the signal is strong enough to be clean, but not so strong as to cause compression or damage. It's a delicate balance. Building on these practicalities, modern VNA systems, like the Agilent PNA series mentioned in the sources, offer a wealth of platform benefits compared to older models,
Making life easier for the engineers.
making complex measurements far more flexible and efficient. For instance, they offer extensive measurement flexibility,
How so?
allowing for incredibly detailed, multifaceted analysis of device behavior. This includes capabilities for up to 64 measurement channels, 48 traces to display various parameters simultaneously,
Lots of data on screen.
16 independent windows for different views, and an impressive 16,001 data points per trace for high resolution. This means you can gather and visualize vast amounts of data in a single setup. They also provide seamless connectivity.
Talking to other gear.
You can easily integrate them with other systems via standard interfaces like LAN, GPIB, and USB.
Usual suspects.
This means you can control them remotely from a central computer, transfer large data sets quickly, and connect to a wide array of peripheral equipment like power meters or specialized fixtures, making them versatile hubs in a modern test environment. A huge advantage, and a truly transformative one for the design cycle, is their advanced automation capabilities.
Automating the tests.
The open Windows environment on these instruments allows for maximum flexibility for automating measurements. Historically, engineers would write code on a separate PC, send commands over GPIB, wait for data, pull it back.
Slow and clunky.
Very. This serial communication created bottlenecks. With the PNA's integrated environment, you can write and execute sophisticated control scripts, whether in VBA, .NET, or COM, directly on the instrument itself.
Running the code on the VNA.
Exactly. This is like having a supercomputer running your test sequence locally, dramatically cutting down on communication overhead, and speeding up complex, iterative test routines by orders of magnitude. Imagine running complex design of experiment sequences or lengthy characterization sweeps in minutes instead of hours. Finally, they boast remarkable ease of use.
User-friendly despite the complexity.
Relatively speaking, yes. Despite their immense power, features like a built-in help system, an intuitive cal wizard that guides you step by step through calibration,
Holding your hand through the delicable process.
and the aforementioned ecal modules significantly simplify the measurement process, even for complex pulsed RF setups. This lowers the barrier to entry for new engineers
Easier to learn.
and allows experienced engineers to focus on interpreting the data and solving design challenges, rather than struggling with equipment setup and arcane commands.
That's fascinating. This level of automation and integration is what truly accelerates the design cycle for engineers,
It really does.
allowing them to rapidly prototype, test, and verify complex RF designs. That seamless compatibility with simulation environments like Keysight Pathway Advanced Design System, or ADS,
Linking simulation and measurement.
means engineers can move effortlessly from designing their circuit in software to measuring its physical manifestation in the lab and back again,
Closing the loop.
continuously refining their designs based on real-world data. It's truly a feedback loop that greatly speeds up innovation, allowing cutting-edge technologies to get to market faster and with higher quality.
Exactly. These integrated capabilities enable comprehensive distortion analysis under modulated conditions, making the VNA an absolutely essential tool for characterizing the linear and nonlinear performance of power amplifiers in today's demanding wireless landscape.
Truly indispensable now.
It's truly a leap forward in ensuring the quality and reliability of our connected world. #tag outro.
What an incredible deep dive we've had today. Wow.
Yeah, covered a lot of ground.
We've journeyed from understanding the fundamental, yet often unseen, role of power amplifiers in our daily wireless lives,
The unsung heroes.
and the crucial balancing act between efficiency and linearity, all the way through to the sophisticated measurement techniques required to characterize their complex, nonlinear behavior under real-world pulsed conditions.
We've seen how modern VNA systems, with their advanced software applications like modulation distortion analysis, arbitrary load control, and digital pre-distortion,
All those clever tools.
are truly revolutionizing how engineers design, test, and certify these critical components. They offer unparalleled accuracy, speed, and flexibility, moving way beyond the limitations of older time domain methods to provide deep insights into phenomena like gain compression and spectral regrowth.
Ultimately ensuring cleaner, more efficient signals that are vital for our increasingly connected world. So what does this all mean for you, the listener? It means that the incredible performance of your wireless devices, from lightning-fast 5G speeds to extended battery life and crystal-clear calls, relies on engineers having an incredibly detailed and precise understanding of these powerful yet tiny electronic workhorses hidden inside your tech.
A lot going on under the hood.
It's a testament to the unseen complexity and continuous innovation that makes our modern conveniences possible and reliable. As wireless communication continues to push the boundaries, moving into even higher frequencies, wider bandwidths, and more complex modulation schemes, perhaps even into, terahertz communication or truly integrated self-healing networks.
The next frontiers.
What new challenges will emerge for characterizing power amplifiers? How might future measurement techniques, beyond even the advanced VNA methods we've discussed today, evolve to meet those demands?
What comes after X parameters?
Right. What will be the next frontier in understanding and controlling the invisible forces that shape our connected world?